Hi, and welcome to a special episode of Competitive Programming. We're going to talk about the disjoint set data structure, and I picked out four programming problems that are pretty easy to solve given this data structure. I'm recording this because we had a winter storm and we didn't get to meet in person, but hopefully this will let us continue solving some problems and figuring out some of the things we need to do that. Uh, Competitive programming, I feel like it doesn't require knowing a whole lot of data structures. There are a few that are really important and that show up. And for these data structures, you need to be familiar with them. You need to know the asymptotic running time of their operations so you can think about how fast your technique is going to be if you use them. You should be able to implement them and adapt them to a new problem, but most of the time, you should try not to spend problem solving time writing up or figuring out a data structure implementation. You should use an existing implementation, like something that's in the collections framework in Java or the standard template library if you're in C++. Or for some, you might have a reference implementation that you use and type in when you have to. And this one's probably simple enough that you could do that. It's a tiny little bit of code you have to write, and it's pretty easy to modify that to solve new types of problems. Here I'm trying to show how the disjoint set data structure works. It lets you have a number of items and keep them organized into one or more sets such that every item is part of one of those sets. It gives you an efficient way to, given two items, tell whether or not they're part of the same set. So G and I would be in different sets, but C and D up here would be part of the same set. It gives you an efficient way to take two sets and merge them into a bigger set, like from here to here, I combine these two sets into one bigger set, and this data structure is really good at that. And of course, you can create new singleton items and then merge those into bigger sets. This data structure is not good as a container. It's not really made for letting you list out elements in one of the disjoint sets, but it is really good at answering the two questions we just talked about. Are these, or doing the two things? Are these two items part of the same set? And merging two sets into a bigger set. It's used in algorithms, common algorithms for connected components in a graph, or for computing one of the minimum spanning tree algorithms. The way it works is for every set, it has a representative element that kind of stands for that set. So like I'm trying to show here, maybe A is the representative of this subset, maybe E is the representative of this one. And it's got a find operation that given any element can find its representative. So here, given I, its representative is E. Given D, its representative is A. And then that lets you tell that these aren't part of the same set. If they were part of the same set, they would have the same representative. So, for example, I is represented by E and H is also represented by E. So that would be a quick way to find out that they're part of the same set. So to implement this, we've got to have a way to implement the find operation. And then we got to have a way to implement the union operation. But uh, to union two sets, all we have to do is pick one element to be the representative of the new larger set. And the common way to implement this gives us a fast, easy to code way to decide who the representative is going to be whenever we put two sets together, whenever we do this union operation to merge two sets. And the way we're going to make this work is we're going to organize the sets as trees, where the representative element is the root of a tree, and all the other elements in that set are descendants of that root. So if you're the root of a tree, you have a point. So every node in the tree has a pointer to its parent element. That's kind of different from how you normally build a tree. Normally, you think of having trees pointing down to the children. But for this one, we just need pointers to our parents. So if you're the representative of a set, you you are your own representative. Your parent pointer could point straight to you. Your children point to you as their representative. Their children point uh, up the tree, so that in general you might have to traverse a few levels of the tree to get to the representative. Each subset is a separate tree in this forest of trees implementation. There's a separate, yeah, tree with a different representative element at the root. So find is not going to be a constant time operation because we may have some paths that point up the tree and have to traverse many levels to, or a few levels to get to the representative element. But union is going to be very cheap because if we've got two trees, once we've found the representative elements, if we've got two separate trees and we want to merge them, we just have to pick one to be the parent and the other one we can graft in under it. And now all of these nodes in both of these trees point up to a new representative that stands for the whole tree. So find may take a few steps to find the representative element, but then actually merging the two trees is just a single pointer change. So that union operation will be cheap. I made an example here to try to show how this works, and I just picked some operations for it. So let's say you started out with a bunch of singleton sets a through G. So they initially are their own representative. They're in sets by themselves. If you wanted to merge A and B, all I have to do is, or actually I did A and D, or sorry, B and D here. So I find their representatives. So B is represented by itself, and so is D. I pick one of them to be the parent, and I hook the other one underneath it. So after I merge their two sets, they look like this. Continuing, if I wanted to union, if I wanted to put together the sets that contain E and F, I find E's representative and then make F's representative point to it. They were previously singleton sets, so now they look like this. If I did the same thing with G and A, I might hook A under G like this. And then from there, if I union F and C, and here it starts to get a little bit more interesting, F is represented by E. C is represented by itself, so I could just hook C under E as a child. And now I've merged those two sets. If I union A and D, well, A is represented by G. D is represented by B, so all I have to do is pick one of those. Here I picked G, and I hooked this smaller tree underneath it. And then last, if I wanted to merge all of these together into one big set, I might take the representative of B. So B is represented by G. I might take the representative of C, that's E. And then I just hook one of those underneath the other. I make G, in this example, I make G the parent of E. And now I've merged everything into this big set. So the union operation might cost a few steps to go all the way to the root of a tree. So if it was a tall, skinny tree, that would be more expensive. But once I've found the representative of two sets, if they're not already in the same set, actually merging those sets is very cheap. To make sure that the find operation doesn't get too expensive, implementations will typically do path compression during the find. Find, I've tried to show a picture here. If you have these long chains of pointers to get to the representative element, and after you've done a lot of unions, you could end up with some long paths in the tree. But path compression during the find operation makes sure that even if you'll occasionally run into a long path, you won't have to keep traversing that long path over and over again. Whenever you do a find, if you have to follow multiple hops to get all the way to the root, it automatically flattens that out so that every node you went through along that path gets modified so it points straight to the root. So it kind of builds in these shortcuts for any finds you might do in the future. So all these red pointers get changed so they point straight to the root element. And again, that's called path compression. If you implemented find recursively, and it'd be pretty easy to do that, then this might be a typical find operation without path compression. If you want to find the representative of X, well, if X is its own representative, or sorry, if X is not its own representative, if its parent is not pointing straight to itself, then just find the representative of its parent and return that. Otherwise, if it is its own parent, or if its parent pointer points straight back to it, then it's already the root of a tree, and you can just return this. I'm showing this recursive implementation of find because if you did it this way, it would be really easy to convert this to a version that does path compression. It's just whenever you bother to go find the representative of your parent, go ahead and point straight to that representative rather than just pointing to what used to be your parent node. So backing up a slide, this little change here will automatically flatten out these long lists of parent pointers. This is a recursive implementation of find, or this one back here was. An iterative implementation could be a little bit faster. So I'm showing that it's not too hard. It is a little bit more work, but it's not too hard to implement find iteratively. So here we just keep following up the chain of parent pointers until we get to a item that's its own parent, and then we return that. But this version doesn't do path compression. If we want to do path compression, we can do that iteratively. We just have to make 2 trips, or at least that's how I normally do it. First, this little bit of code goes and finds the node at the very top. So it keeps following parent pointers until it finds a node R that is its own parent. And then we take another trip up that same chain of pointers, but filling in the shortcuts this time, making every node along that path point straight to its parent. So this code isn't exactly what I normally use for this, but it's the kind of thing I use for my disjoint set implementation, iterative implementation of find that automatically does path compression. To get the absolute best performance out of this data structure, people will normally do path compression and what they call union by rank. The thing that slows down this data structure, and it doesn't slow it down by much, but the thing that can make it a little bit slower is if you get these long, tall trees that don't get flattened out until you start doing find operations on them. When you do the merge, you can try to make sure that trees don't get taller as you do the merge. So here I'm showing if you had a short tree and a tall tree that you were going to merge together. Well, this is a bad way to do it because the tree, if you make the shorter tree the parent and the taller tree the child, then all the paths in this child get a little bit longer. Whereas if you do it this way, if you put the shorter tree as a child of the parent, then the overall height of the tree doesn't get any worse. So it's always a good idea to merge shorter trees under taller ones. But you can't always do that. If you had 2 trees of the same height, when you merge them, the resulting tree is going to be 1 link taller. So only do that when you have to. And you can do this by keeping up with what they mean when they say rank, a number that represents an upper bound on the height of the tree. And then whenever you merge 2 trees, you can think, well, is it this case? My tree didn't get any taller, or is it this tree case? My tree might have gotten 1 unit taller. And in doing that, you can keep up with, again, an upper bound on the height of the tree every time as you do the merge operation. For my implementation in competitive programming, I usually don't bother with this union by rank heuristic. If you want, like I said, the absolute best asymptotic performance, you have to do this. But for competitive programming, as long as you implement disjoint set with the path compression, you'll have performance that's fast enough for about anything you might need to do. The reason I mention this union by rank trick is even if you don't do that, you can use some of the same tricks to compute other stuff as you build your disjoint set data structure. Like instead of keeping that rank value at the root of every tree, you could keep the size of the tree at the root. Every node could carry around a field that's used to represent its size. And then for any root nodes, you could just make sure that they always reflected the new size of that tree whenever you did a merge. And this is pretty easy to do. I'm trying to show an example here. If I had a tree of size 3, and I was unioning it with a tree of size 6, well, the new tree is going to be 9. uh, kind of the size of these two trees put together. So I could update that at the root. I wouldn't have to worry about keeping that value current at the internal nodes. I would just need to make sure that whoever was at the root always had the overall size of the tree. And then if you wanted to know how big of a set you were in, you just have to go find your representative and look at the size field here. One of the problems I picked out for tonight benefits from this. So, and it's pretty easy uh, refinement to add to this data structure. Another thing I'll say about how I typically implement this is, well, I'm usually programming in C++, so I could use pointers for this, but I try to avoid pointers in competitive programming if I can, because they're a little harder to debug. If you printed out the value of a pointer, it doesn't really mean anything. It's not going to it'll be a little harder to fix an error if you got one of the pointers wrong. Normally, I would do this using an array of items, and I would just use the index of an item in the array, kind of like a parent pointer. I'm showing here how I might do that. So I've got items 0 through 9. Every item has an array element, so this is the 9th element, and that array element is just an integer that says who my parent is. So if you're element 9, element 7 is your parent, and I use a -1 for elements that are singleton, for elements that don't have a parent. So if you're 9, you're in the 7, you're in the same set as 7, and 7 has -1 as its parent, so it's the root of that little tree. It's its own representative. If you're 3, then you're in the same set as 7. So this is a little 3-element tree. And here, if you're 4, you're in the same set as 0, which is in the same set as which is the root of that set. So it's the representative. So this is nice. I've said a couple of times because it's probably a little bit easier to debug, and it's easier to initialize. If I had to fill in an array of pointers where each one pointed to itself, I might have to write a little loop to do that. But here I can probably write a single assignment to fill in an array of items all full of -1. So that's all I've got to say about disjoint set. The problems I picked out should benefit from this implementation, and hopefully they'll be pretty easy to solve given a working implementation of disjoint set. If this is the first time you've implemented it, I would try to implement it in a way so that you can pull it out of your code when you're done and save it in a little code library so that in the future, if you have to use this to solve another problem, you don't have to figure out how to write your own version of something like find. You can trust that you did it right the first time and just reuse that implementation. Good luck solving tonight's problems. I'll be around on Zoom if you want to stop by and see me. I'll talk to you then.